Okay, here's video 1 for the SHRATEY examples 3 notes. Also have your green SHRATEY sheet out nearby to help you. So the S is for simplifying. That means we want to factor and then cancel common factors where possible. So we start by looking at the numerator and seeing if it can factor. What multiplies to 2 and adds to -2, and nothing will work. So that means the numerator can't factor, and therefore it can't simplify. And therefore, again, there's not going to be any holes or discontinuities in our graph. So R is for roots. That's where we set the numerator equal to 0 and solve, but because we can't factor it, we can't solve it. And what that means is, if you can't factor and solve, then there are no roots. Okay, no x-intercepts. So it will never cross the x-axis. A is for asymptotes, specifically vertical. So that's where you solve your denominator. Set it equal to 0. Solve it, you get x equals -2. That is a vertical asymptote, which I'm going to sketch in right here. T is for tangent and together. You're looking for squared factors in the numerator or denominator. So let's have a little discussion about the difference between factors and terms. When we're looking for squared factors, an example would be this. Factors are things being multiplied. So in this example, I have this group x minus 3 is a factor, and this group x plus 4 is a factor. And this is an example of a squared factor. If we have something like this squared, this x squared term is being added. Okay? If something is being combined with other terms with addition or subtraction, this is called a term, not a factor. It's not being multiplied by anything. So this squared doesn't count when we're trying to determine behavior at the roots or behavior at the asymptotes. But this kind of squared does, because it's x minus 3 times x minus 3 times x plus 4. Each of these groups are factors because they are being multiplied by the other groups. And if one of those is squared, then that does determine behavior. So we're only looking for squared factors in the numerator or denominator, not squared terms. So going back to this particular problem, I'm going to say that there are no squared factors in the numerator because there aren't. There's a squared term, but we don't care about that. There's also no squared factors in the denominator. E is for end behavior, so we set up the ratio of our leading terms. So that's the x squared over the x. Now this is top heavy. And this means we're going to have an oblique or slant asymptote. So we've already talked about vertical and horizontal asymptotes, right? Those are easy to write the equations for. It's either x equals a number or y equals a number. But a slanted line is not that simple. It's a linear equation of the form y equals mx plus b. And so we have to figure out how to generate that equation. And the way we do that is we divide the numerator by the denominator. We can do this with polynomial long division, which we reviewed earlier in the year. We could do that process, but what we're going to do instead, because all of our denominators are going to be linear factors, so we can use synthetic division to generate that quotient instead. So that's going to start out like this. I put the 0 of my denominator in this little box. That's going to be -2, because that's the value that would make this 0. And then the coefficients of my numerator go next. So that's 1, -2, 2. And how I begin is I drop the first term, 1. I multiply these two things, -2 times 1. That's -2. That goes here. Then I add vertically, and that gives me -4. Now, technically, if I was to continue, I would do this next. That -2 again, times -4, which is 8, and then that gives me 10. Now, this very last number is always the remainder, and for our purposes, we don't care about the remainder. We only care about these first two things. That's going to give me the coefficients for my linear equation. That's going to be my asymptote. That's what's going to give me the shape. The remainder is not important to me for this purpose. So the way we get our line is we add in our x variables back in 1 degree less than we started. So we started with a degree of 2, and after we divide by a linear factor, we're now at a degree of 1. So this is 1. This is going to be x to the 1, and then x to the 0. Remember, x to the 0 is just 1, so we don't need to keep that. So here's my final answer. Y equals 1x to the 1, or just x, and then -4. So that's my slant or oblique asymptote. And you are free to graph this however you feel comfortable. You could graph the y-intercept, and then the slope is 1, and you could count up 1 over 1 over 1. What I like to do is find the two intercepts. So the y-intercept is where you put 0 for x. So just cover that x up, imagine it's gone, and you're left with y equals -4. And then for the y-intercept, or sorry, the x-intercept, you just let your y value be 0. So imagine that is 0. And you're going to solve for x by adding this 4 to both sides. And so x equals 4 when y is 0. So I'm going to graph those with open circles. They're not actually points on the graph, so I'm not going to make them solid. They're just the points for my asymptote. So 0, -4, I have an open circle here, 4, 0 here, and then I'm just going to connect those with a dashed line. All right, and there is my slant or oblique asymptote. And the last thing I want is my y-intercept. I'm going to find that by plugging 0 in for all of the x's in the original function. So that's 0 minus 0 plus 2 over 0 plus 2. That's 2 over 2, or 1. So my y-intercept is 0, 1. And I'm going to graph that now. Now, before I talk about the basic shape, what happens when I have an oblique asymptote, let's just review real quickly something we've talked about before. When you have a vertical asymptote, we talked about how the end pieces are this curved shape like this, right? It's kind of like, well, not kind of, it's like 1 over x, the parent function 1 over x. Once we add a slanted asymptote, what that's going to do is take this and pull it up. So imagine now I have this angle here. Instead of having this shape that's like a really strong L, instead what we're going to have is this shape right here, where it's still drawn as x goes out to infinity. The y values are still drawn towards that asymptote right there. So, and remember, we're just sketching. We're not going to overthink this. We don't have to be super particular. I know that my basic shape here is going to be that curved shape in here. And I know it has to go through my y-intercept. So I'm just going to curve it here. If I was trying to be very particular, I would do some test points to get a better shape, but this is good enough for our purposes right now. And then the second part of this graph is going to be mirrored down here, and it's just going to fill in the space between the asymptote, the other ends of the asymptotes. All right, and so there's our basic graph. All right, so number 2, we're going to start again by trying to factor the numerator. What multiplies to 2 and adds to 1? Nothing works. So again, can't factor, so we can't simplify. Can't simplify, so there's no wholes. Can't factor, so there's no roots or x-intercepts. For the numerator, I won't be able to solve it. There will be no real solutions to cross the x-axis. All right, so the first thing we can do is our vertical asymptote. Set your denominator equal to 0 and solve. That gives me x equals 3. So I'm going to graph that. T, I'm looking for squared factors in the numerator. There are none. And no squared factors in the denominator. So remember, this is a squared term, something that's being added or subtracted to other things. I'm only looking for squared factors, things that are being multiplied by other factors. All right, and behavior, our leading terms are top heavy again. So we know that we are going to need to do the synthetic division to find our equation. So this time I'm going to be putting positive 3 in my box, right? That's the 0 of the denominator, the number that would make it equal to 0. And my coefficients for the numerator are 2, 1, 1. So I drop down the first term. Now 3 times 2, so I'm multiplying these two things. 3 times 2 is 6. Put that here, add vertically, and I don't care about the rest of it. So my equation is going to be y equals 2x plus 7. I'm going to find my x and y intercepts for that. When x is 0, y is 7, and when y is 0, so imagine I have a 0 here, I subtract 7, then divide by 2, so negative 7 halves, or negative 3.5, 0. And I'm going to put open circles there. That's not completely straight, it's going to bother me. Make it a little bit better. Okay. It's not much better, but we're moving on. So 0, 7, open circle, and then negative 3.5, 0, open circle, and then my dashed line. And you can see how it's kind of going off here. So, and I need it to intersect here. So I'm just going to extend those. On my PDF in the Google Classroom, I did the vertical scale by 2. So you might want to do that to fit it on your graph better, but I just didn't do it here. All right, so then our y-intercept, put 0 in for all your x's. 0 plus 0 plus 1 over 0 minus 3. That's going to give me negative 1/3. So 0, negative 1/3 is my y-intercept. And that point is on our graph, so I'm going to do a solid line there, or solid dot. And now my shape is going to approach my asymptotes. It's going to be this curved shape, and then one mirrored over here in that area. Okay, and I am going to make a second video for the back, for the other two problems.